Welcome to my talk on secure and scalable document similarity on distributed databases. I'm going to present joint work with Lennart, Adria, and Borja. Let me first introduce the setting we're working in. In distributed text classification, we have two servers who share a database of labeled text documents. We also have a third party, a client, who has an unlabeled text document, which she wants to classify. Now, as you might know, there's a general concept called multi-party computation that allows us to distribute any centralized computation that we could perform in the clear with a trusted third party to a multi-party computation protocol that reveals only the result, but not the party's individual inputs. So this could mean that we're already done, right? Because we could just apply this concept using a general MPC compiler to our text classification problem and reveal the result to the client. The problem that this generic approach is very inefficient. So using a general MPC compiler comes with a huge overhead in terms of communication and computation, so we need to do better than that. And we do that by looking at the individual phases that our algorithm has. So for the k-nearest neighbors text classification algorithm, which we're going to use here, we can identify the following three phases. First, we need to transform the text documents that we have as inputs into something we can work with, that is, vectors over real numbers. Second, we want to perform a comparison of the query document with each of the documents in the database and assign them a similarity score. Finally, we're going to sort the documents by the similarity to the query document and reveal the class that is most common among the k-nearest neighbors of the query document to the client. So how does this map to our distributed setting? Well, we can make the observation that for feature extraction, most of the data that we need is in the database. So this can be done between only the two servers who have the documents, but without the client. What we're going to do in practice is we're going to perform a pre-computation step that reveals some statistics about the dataset to the client and all the other parties, who can then locally perform the rest of the feature extraction phase. For the scoring phase, we can see that it always only involves one of the servers and the client, because to compute the score of the query document compared to one of the database documents, we need to only involve the server actually holding that document. So we can split up the scoring phase into two-party computations. Finally, the only computation that actually needs to be performed between all three parties is the ranking phase. And for that, we're going to use a general MPC compiler called MP-speeds. And that's why I'm not going to go into much of the details of this phase, because it's not very interesting. So this talk focuses on the first two phases, feature extraction and scoring. So let's talk about feature extraction. Here, as I said, we want to transform a document into a vector over the reals. We're going to use the textbook TF-IDF feature representation, which consists of two parts. First, TF is the term frequency that simply assigns to a term the number of occurrences in the document. Secondly, the inverse document frequency. It's used to weigh down the impact that very common terms have on the score. So it's the logarithm of the inverse of the amount of occurrences of the term in all documents in the database. So the number of documents that term appears in. Finally, the document vector is just the product of these two for each term in a public vocabulary. As you might already see here, the only part of this TF-IDF feature representation that depends on data from more than one party is the denominator in the IDF definition. So here we want to compute the number of documents that contain a certain term. And for that, we have to look at the entire database. What we're going to do is we're going to reveal that count in a differentially private manner. So let's have a quick recap what we mean by differential privacy. We say that an algorithm is differentially private if the output doesn't change too much whether we add or remove a single element in the input set. So more formally, the probability of observing a certain outcome should change only by a factor of e to the epsilon, where epsilon is called the privacy budget. So our goal is to perform a two-party computation between the two servers and reveal differentially private IDF values at the end of that. Now, we could use a general differential privacy mechanism, such as the Laplace mechanism, and apply it to that problem. The problem with this generic approach, again, is that the noise scales with the number of values you want to reveal. And since the number of IDF values you want to reveal is equal to the size of the vocabulary, that is quite a lot values. So those will be very noisy and not very useful in practice. Instead, what we're going to do is we're going to look at the distribution of words that they have in natural occurring text. So these usually they follow a power law distribution. That implies that they have very few very common words and also very many not that common words. If we look at the corresponding IDF values to this distribution, we'll see that it quickly converges to a maximum value that we're just going to call IDF0 here. And so that means after looking at the first L terms, we can assign all the other terms that are less common than the first L a default IDF value, which corresponds to a default count. So far, we didn't even consider the database. We just defined a default value that we assign to most of the elements in the vocabulary. But how do we select the top L words in our database? For that, we're going to use the exponential mechanism, and it has been shown that it is optimal for top L selection. So what it does is samples words proportionally to the exponential of their actual count. And once we have sampled the word, we can reveal its count where we disturb the count with a Laplace mechanism. So doing that L times reveals that, an approximation of the top L terms, so the L most common terms, where the counts have been distributed, have been noised with Laplace noise. So now the question remains, how do we perform the sampling in MPC? So this mechanism, I just described it in the clear, but not how to implement it in MPC. What we're going to do is a tree-based approach that we call the Bernoulli tree. So we can write the vocabulary that we have. In this example, it's V1 to V4 on the leaves of a binary tree. On the leaves, we also write the probabilities we want to assign each of these leaves to be sampled in the beginning. So this time we want V1 to be sampled with probability 0.4, for example. Then on each inner node, we just sum up the values on the children. Now, in order to sample an element, what we do is we traverse the tree from the root, and at each node, we perform a Bernoulli trial, weighted with the weights written on the child nodes. So for example, this time we could get the value V2. And now we have to make sure that we're not going to sample that value again. We want to sample without replacement. So the way we're going to do it, we're just going to remove subtract the value that's written on the leaf that we just sampled from all the nodes to the path to the root. So this would be the result. And now the next time we sample something, it's going to be a different leaf. For example, leaf V3 this time. As you can see, the leaf V2 is deactivated. Its probability is set to 0. It cannot be sampled again. Now, how can we do this tree traversal in MPC? For this, we're going to use a generic approach based on ORAM. So if we represent each layer in the tree as an ORAM of doubling sizes, then we need a total of O of L accesses, and the total number of ORAMs is the depth of the tree, which is log V. So we're going to implement that in oblivc and use different ORAM constructions depending on the size of the level of this tree. So this concludes the feature extraction phase. So let us go on to the scoring phase. Here, a quick recap, we want to have a measure of similarity between two feature vectors. And now these feature vectors will be TF-IDF vectors. The standard approach here, again, is cosine similarity, which is defined as follows. It's the inner product of the two vectors divided by the product of their lengths. Now, two observations we can make here. First, we can normalize the vectors locally. So that way, the cosine similarity simply reduces to a secure inner product. Secondly, the vectors, if they are TF-IDF vectors, then they will be very long. So they will have length of the size of the vocabulary, but also very sparse, because words that do not appear in a single document will have a value of 0. And we're going to make use of that sparsity to speed up our secure inner product. Inside our protocol, as a black box, we're going to use a secure protocol that does not use sparsity. And so there are many approaches you can take to have a secure inner product protocol. We're going to use one based on oblivious transfer, but you could also use one based on homomorphic encryption or other approaches. So at the end of this black box secure inner product protocol, we're going to have additive shares of the inner product of the vectors we put into it. Now, if we take our sparse vectors, in this example, they will have length 20, but in reality, they will be much longer, like 150,000 or something like that. Here, the colored boxes represent non-zero values. Zero values are represented by white boxes. And you can already see that the result of this in a product will only depend on values where both parties have a non-zero value, because all the others will be multiplied by 0 and so will not contribute anything to the final sum. So how can we make use of that? We're going to let the parties locally permute the vectors using permutations, pi1 and pi2, that are correlated in the sense that they shuffle values that match on both parties to the same position. At the same time, we require those correlated permutations to shuffle all the non-zero values to the beginning of the vectors. So in this example, we have a total of 7 non-zero values. So we require the output of the correlated permutations to shuffle the non-zeros among the first 7 values of the outputs. And as you can see, what was index 17 before is now index 5. And so the matching indices are shuffled to the same position. Non-matching indices are lined up with a 0. So the result would be the same, and we still have correctness. At the same time, shuffling all the non-zeros to the beginning of the vectors gives us an advantage because we now can just shorten these vectors and pass shorter vectors to our dense, secure inner product protocol, which improves communication and computation in practice. Now, the only question remains, how do we get these correlated permutations pi1 and pi2? So how do we generate them in a multi-party computation? The way we did it in this paper was based on private set intersection. So we use circuit-based PSI to perform intersection of the non-zero indexes of both parties, and then send the correlated permutations to each of the parties. There are more efficient approaches, however, and we take a look at them in a follow-up paper that appeared at CCS last year. There we also have applied to other machine learning tasks. Here we focus on KNN. So that concludes our scoring phase. And now the question is, of course, how much does it, using the sparsity, improve our computation times? And also, how much does the accuracy decrease because of the differentially private pre-computation that we do? To find out that, we conducted an experiment on a data set of 28,000 Amazon product reviews. And here the goal is to infer the category of the product by just looking at the review. We assume a public vocabulary of 150,000 words, which is about the size of a large English dictionary. And we perform accuracy experiments on plain text data in a local setting and running time experiments in the Azure cloud. So for feature extraction, if we look at the number of non-default values, so the number of values that we sample in our tree-based sampling approach, then, and look at the running time depending on that, then we will see that it barely impacts the running time for all the values we tested from 1 to 128. So the time stays under 10 minutes for all cases, and that's pretty good for a one-time pre-computation. On the other hand, we want to know how does the differential privacy that we introduced, so the noise introduced by the differential privacy, impact the accuracy of our scoring. So on the right side, we experiment with different privacy parameters epsilon and also different training set sizes. And you can see that the accuracy decreases, of course, as we decrease the privacy budget, but this can be made up for by increasing the training set size, which is what our algorithms allow for in the first place by allowing more than one party to join the computation. For the scoring phase, we looked at the effect of sparsity, and that we did on synthetic data. So we wanted to see how much do we improve compared to the dense setting, and also how many vectors can we permute at once before this becomes too inefficient. So increasing the batch size allows us to compute less correlated permutations, so saves time on that part, but it also decreases the sparsity of the batch, which means the permutations will be longer. So here you can see that a batch size of 16 is optimal for uniformly distributed data. But for example, on the reviews data set, so on real world data, this increases to a batch size of 512 in the LAN. Overall, the scoring phase needs about 20 minutes of computation, and a full KNN classification we can do in about 40 minutes. To conclude, we have learned that we can make distributed document classification feasible by revealing some differentially private data about the dataset in a pre-computation phase. And so this allows us to gracefully relax privacy and find a middle ground between MPC security and just differential privacy. At the same time, if we have sparse feature representations, we can use that to speed up similarity computations. And we applied that here to the scoring phase of K and N, but there are also other applications, and it might be interesting beyond our work. So with that, let me conclude. Thank you for your attention, and I'm happy to take any questions.